Hey everyone, today I want to show you this simulation game I made. It's sort of a game, sort of a simulation. It is something that is inspired by an amazing video um, by Stephen Wolfram. It's called Computation and the Fundamental Theory of Physics, and it's like 1 hour long video, but I'm going to give you kind of the short version. It discusses how the universe itself might work, uh, especially assuming it might be a simulation. I don't know how many of you are familiar with Conway's Game of Life, but if you aren't, I highly recommend you look up Conway's Game of Life. It's this thing here. I'm going to show you now. So Conway's Game of Life is a simple simulation.
This is exactly. Look at this path. It's going to stay alive.
It basically it's called a cellular automaton, and what it does is it simulates.
Now you can see it looks like it's rotated itself right horizontally or vertically, and the same again. You see a reappearance of a pattern.
So this is a cellular automaton. It's basically an algorithm that simulates a grid of quote-unquote cells, but given a specific set of rules. And for Conway's Game of Life, the rules are very simple. And I'm going to show you Conway's Game of Life rules. And there are just 3 rules, and these 3 rules can create very, very complex simulations. Here are the rules. Any live cell with 2 or 3 live neighbors survives. Any dead cell with, maybe let's look at an image as well. So any live cell with 2 or 3 live neighbors survives. So this middle cell, see, it doesn't have 2 or 3 neighbors, so it dies on the next generation. Rule 2, this cell has 2 neighbors, so it survives on the next generation. Rule 3, this cell, any dead cell with 3 live neighbors becomes a well, actually, this one is this rule. All other live cells die in the next generation. So if it has too many neighbors, it also dies. See, on the next generation, it disappears. And any dead cells with 3 live neighbors becomes a live cell. This one. It has 3 live neighbors, so it comes into existence. So these are the only rules that govern Conway's Game of Life. But these very simple rules can create very, very complex simulations. Let's see some very, very interesting ones. Let's see if we can find. So just with those rules, you get stuff like this. All right, so now you kind of get the idea of what Conway's game of life is. It's a cellular automaton based on a fixed set of rules. These rules here, very simple rules that give rise to very complex behaviors. This combined with Mr. Stephen Wolfram's video, eye-opener video. I highly recommend anyone to watch the entire thing. Led me to want to make this simulation program. And well, to get back to Mr. Wolfram's video, he's basically discussing how the entire universe might be such a simulation. Of course, it's not two-dimensional like Conway's game of life. There seem to be multiple dimensions. Like our universe isn't just three-dimensional. Like, for example, gravity might stem from a fourth dimension. Anyway, stop this. Anyway, to simplify things, I wanted to keep it two-dimensional, but his video discusses how the universe might be a simulation, but instead of using a grid, it might be using something called a hypergraph, and with a graph, of course, you can simulate any number of dimensions. You're not restricted to 1, 2, or 3 dimensions as you would with a grid. And he discusses how the universe might just be a hypergraph of simulated nodes that interact with each other, similar to how the cells interact with each other in Conway's game of life. And somewhere at the beginning of the video, he explores rule sets in one-dimensional space. Well, 2 dimensions if you take time, and like these are the rules that he generates, and he's exploring the entire space of rule sets in one-dimensional space that can create further generations as you go through time. Time is like the vertical axis, and space is just the horizontal axis, being a one-dimensional space. And he explores, like, this rule set here generates this thing here, and as he explores different rule sets, he can get different patterns in one dimension. Now, of course, Conway's game, this is one-dimensional automaton, and he basically uses a program written in Wolfram's language. I forget the name. Oh, Wolfram Alpha, right? And the Wolfram language. So he generates. He has an algorithm that generates these rules. This is called Rule 90 because if you take the binary representation of this rule, it forms the number 90. And he goes through all the possible rules up to 255, I think, and see what each of them generate. And I was super inspired by this to create a rule set. To create a generating program that is able to explore the space of rules in 2-dimensional space instead of 1 dimension. This is interesting to look at, but it's static, it being 1-dimensional plus time, sort of. It doesn't really move. So I wanted to create a 2-dimensional one because Conway's game of life is a 2-dimensional simulation, not 1-dimensional like what he's showing here. And I wanted to create a program that can explore the entire 2-dimensional space of rules, and they can get quite complex. Conway's game of life is a subset of this entire space of 2-dimensional rules, and this is what my program does. It can explore that, and the way it does is we have a seed, and from this seed a rule is generated. The bigger number is the rule. It's this rule here, the rule being simulated. So 42 generates this rule. I won't go into detail into how the rules are generated. They're not just that they're generated from the seed. So 42 will always generate this. 43 will generate a completely different rule. Now you might ask, why don't I just randomly generate this rule here? Well, I wanted to have a very simple way to refer to these rules. So instead of referring to this rule as rule 3827 blah 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 blah, which is a mouthful, you can just refer to this rule as rule number 42. It's the rule that seed 42 generates it. That's why we have seed and rule, and I'm not just directly generating rules. It also allows you to just increment this seed and get a wildly different rule, because rules themselves are kind of like programs. The rules are the numerical representation of this thing here, and that means that adjacent rules, if I just change this 2 to a 3, will generate very, very similar, almost indistinguishable simulations. And exploring this rule space by just incrementing this digit here continuously, it would yield very boring results that change very, very slowly. And in order to keep the program interesting, I'm like, okay, I want to generate wildly different rules, but have them be consecutive in some way. So they're always generated from a seed, and you can always increment the seed to get a very different rule. Now, believe it or not, Conway's Game of Life is one of the rules that you can have plugged in is Conway's Game of Life. So what kind of rules can we have? Well, let's just change density to 4. Let's say 14. That will create. Let's change the simulation step to 5, so you can better see. So 14. This is the density of 14. It populates our initial state with 14% dots, and now the rule decides what the simulation does with that 14%. So it decides to grow these dots into like further structures. It's a simulation that well, let's get just 1%, or maybe 0.1%, and let's change the simulation speed, make it 1 step per second. So this is what the simulation does. It grows these dots into these structures that then merge. It's easier to understand if you lower the density so you can see what happens to each dot. So, and of course, as the screen fills with these structures, it kind of descends into chaos. But you get the idea of what this rule does. Now this is a completely randomly generated rule. It looks super orderly because it's just starting from one dot and growing and expanding. The rules are symmetrical, by the way, symmetrical and mirrored. It's hard to explain what that means for now, but keep in mind they have a bias for symmetry for reasons that I won't go into right now. But you can contact me if you want to know more about it. And now let's go to rule 43 and see what that looks like. So it does something similar. It grows these things. 44. More of a checkered pattern. Now you might think, oh, it just generates patterns like these. Not necessarily. It's not always a growing Oh, these don't grow. Oh, I never realized that. This is very interesting. So unlike the other structures, this structure doesn't grow infinitely. Let's find a density that only yields 1 point. So maybe 2. Yeah, that's 1 point. Let's increase simulation speed. 0.3. So this structure doesn't grow infinitely. This is, it grows, it grows, it grows, it grows. Oh no, it does grow infinitely. Okay, 45. Now you might think, oh, it just generates these growing fractal thingies. That's not true. There are numbers, there are seeds that behave in completely different ways. And I have here at the top a set of presets that you can choose from. Now each preset will populate the seed and the density with a different value, and they can get very interesting. Conway's game of life is actually this rule. I don't know the seed for it. I don't even, there might not exist a seed for this rule. So you can also bypass the seed and override the rule and specify the rule directly. And this is the rule for Conway's game of life. Let's increase its speed. And you can see gliders as well moving around. So Conway's game of life is a rule in this bigger simulation that I called any game of life, because you can literally generate any rule set. And there are other rule sets that are interesting. Conway's game of life is just one of them. You can do arcade, which is seed 76, and it creates this very interesting blinking pattern that you would perhaps see in an arcade. And from what I can tell, this pattern isn't repeating. It keeps generating new shapes. Now, I haven't studied it for long enough. Perhaps it starts repeating at one point, but right now it's not repeating. It seems like every iteration is a different pattern. Maybe it's repeating, but its repetition cycle is pretty long, maybe. And I call this pattern arcade. It's seed 76 with density 0.025. Cannibalistic rhombuses is basically these structures that keep growing, and if they touch something while they're growing, their volume increases, but they tend to want to keep a rhombus shape, you will notice. Despite the chaos that goes inside them, they have a tendency to stabilize into a rhombus shape, and it's extremely weird. I haven't even the slightest clue why this happens. Despite the immense chaos that's inside them, they're not growing, they're not expanding further into like chaotic shapes. They on average keep a rhombus shape. Let's restart it again. See, they start off, this thing tries to stabilize into a rhombus shape, and in doing so touches this other rhombus, and it kind of eats it. Very interesting. I can't even begin to imagine what causes this to happen, especially considering the simple rule set. which is just this number. Dancing cyclic squares, that's the name I gave to this seed, C227 with density 0,025. This density 0,025, I usually use this density when I just want one starting cell and that cell grows. It's good for rules that keep growing from one single cell. And again, this one creates pretty complex patterns. I'm not sure if they're repeating. They seem repeating. A checkerboard rhombus is just a rhombus that grows in a checkerboard pattern. I think it turns into chaos when it unifies. Oh no, it doesn't. And I think that's it. That's kind of the end of it. It repeats from here. Cracked ice. That's what this pattern does. Density 55. It starts from chaos and stabilizes into something like this. White rhombuses. But then when they hit each other, chaos. Just soldiers, because they kind of remind me of marching soldiers. Square mouths. Call this kaleidoscope. It's basically a growing pattern. But it reminds me a tiny bit of a kaleidoscope because of its symmetries. Supernova. C24 with this density. Exploding marching soldiers. Because when they meet, boom, explosion. Exploding spaceships. They kind of look like spaceships that are being destroyed. Laser guns. Still kind of marching soldiers. French kissers. And that's because of these structures here. They look a bit like they're tonguing each other, I suppose. Mouths, again, very similar. I think this stabilizes into a mouth, if I remember correctly. Yep, there we go. Growing diamond. Growing corners. I think the density is wrong on this one. Okay, I think I input this pattern wrong. Ignore it. Oscillators. And I think that's because eventually the simulation stabilizes into just these repeating. These structures repeat. That's why they're called oscillators. This has a 2 period, obviously, but this has a higher period. Now oscillators with periods higher than 2 are pretty rare. That's why I saved this preset. I thought it was interesting that it oscillates with a frequency that's higher than 2. Have amoeba. Let's increase the speed. Maybe increase it further. Well, it looks a bit like a microorganism that moves around and swallows food. You can even see it swallow these dots and then retreats after it swallowed them. And it grows in size as it's eating stuff. Thought it looked pretty cool. Seed 249. Next. Snowflake pattern. This doesn't seem correct. And the seed might be wrong for this one. Ignore it. Or maybe... No, it doesn't seem correct. Lonely Traveler because of this little guy. Let's increase, slow it down a bit, I mean. Let's restart it. Yeah, Lonely Traveler. It almost looks like it's leaping like a frog, but then it hits this thing and creates these marching soldiers. Checkers. And yeah, these are all the presets I have. There are a bunch more seeds here in the description, but what I'm interested in finding eventually is a rule set that simulates the physics we are accustomed with. I'm sure it's somewhere out there in this rule space. And I think anyone can just go through these rules and explore what they look like. And do post them here in the comments if you find any seeds with interesting behaviors. Like a lot of them you will recognize. There are a lot of patterns out there that keep growing. Those usually require small densities like 0.005, or there are a lot of patterns that look like the amoeba. There are just these structures that grow in size in time. What else? There are a lot of blinking patterns, so people with epilepsy, if you're prone to epileptic seizures, be mindful of that. Yeah, but there are also a lot of very unique ones, unique patterns, like this rhombus one. They're very unique in behavior. You don't see them often. They're very rare, so every once in a while this simulation space surprises you with something completely new and unexpected, like this thing here. Like, there is no code that codes for these big squares, these big what are they, 3x3 squares, I think. And yet this seed creates 3x3 squares, all evenly spaced with a tiny little space between them. It's just amazing, the fact that this can happen completely randomly. So yeah, go ahead, explore the simulation space, post any cool seeds you find. And I think that concludes the basic introduction. There are also advanced features in this app. You can specify a starting state. So let's switch to Conway's game of life, right? So this is Conway's game of life, but we don't want it to start in a random state. We want, let's say we drew a bunch of gliders and we want it to simulate this thing. Well, what you can do is you can save this gliders and then Google something called PNG to base 64 encoder. I usually like to use this one here. And then gliders, and then upload your photo and it will turn it into this base 64 string format, which you can then paste here. And there we go. We're now using the picture as the starting point of the simulation. It has to be black and white, by the way. And if it's smaller than this size here, then it will tile it. It will keep repeating it. You can also create very custom rules. So you can basically program new rules from scratch. And this is what this field here does. Instead of specifying a number here, you can specify code here, and I will power up some code. I will plug in some code here so you can see what I'm talking about. It completely changes the rules. And here is the code. It basically is like the state, the rule, and then what action it takes. It's a bit complicated to explain, so I'm just going to do that, and I'm going to, so I plugged in the rule, so now this is the rule, not a number, or this rule itself is encoded as this, by the way. So once you plug in your code here, it gets represented as just a number up here that you can always copy paste. But this field here is designed so you can manually code the rules. That way you can create very interesting machines with it. And for that rule I have a starting point as well. And this rule is meant to move a glider of a specific shape. Like I manually designed it to do that. And this is the quote-unquote glider for this rule. It's like I wanted to create a structure like the Tetris T-shape, the little Tetris T-shape. And then I wanted a rule set, and I was like, okay, what rule set would move this T-shape across the screen? And I handmade that rule that moves the T-shape. So you can treat this as a puzzle of sorts. If anyone is ever interested in how to create these custom rules, what these numbers mean, then just message me and I will explain to you how to code for this, how to code custom rules. And yeah, if you're not interested in the coding part, you can always just explore the random seeds. In order to explore the seeds, you need to make sure these are clear, and then you can just proceed to look at all sorts of crazy seeds. A lot of the times when you input a seed, you will notice, oh, it's very noisy, I don't understand what's happening. In those cases, try decreasing the density. Oh, I'm sorry. This is still Conway's. I thought I recognized Conway's shapes. Make sure this isn't checked, because it was overriding any rule the seed generated with Conway's rule. So yeah, no Conway's rule. Yeah, you might get seeds that are very chaotic and you don't understand what's happening. Try lowering the density, and then you can better understand what's going on with the rule. Sometimes the rules are not these growing rules. They actually shrink. They keep a constant size, constant density of points on screen. Let's see if we can find Well, you can use auto increment to explore the seeds. It automatically increments each seed. Oh, like for example, this seed is not one of those growing seeds, even though it has like 1 point, which means you can safely increase the density to, I don't know, maybe 33% and see what happens. A lot of them seem to die off based on the rules, unless they're into like organized into square patterns or these oscillator shapes. So yeah, this is the basic introduction to this app. I know it seems like a very complex app, but it can generate some very, very interesting things like I showed you. Conway's Game of Life is one of them, but a very different one is this arcade rule set. So yeah, experiment with it and hope you have a lot of fun with it. See ya. Bye.